Last time we met together, we started section 6.4, which is about proportional reasoning. And we talked about the idea of making sure that when we set our problems up that we do so in a way that compares things accurately. So either comparing from numerator to denominator or comparing from one side of an equation to another side of the equation. And we had come across a few examples of proportions, and I think we did two of them. We did one of them in class, actually, this one, with the number of days that he had a vacation compared to the number of months that he was working. We even talked about the fact that there's definitely more than one way to set up a problem like this and all arrive at the same answer, equally correct. So we're going to do a few more examples that are like this. This one is an example of scaling. So on a map, you guys don't even know what a map looks like, do you? I'm a little concerned for you. But on a map, one that you actually read in paper form, this particular person has a city map for a park, has a length of 4 inches, and the park has an actual length and width of 500 feet and 300 feet. And so the question they're wanting to know is how wide was the park on the map? Okay. So what I need you to look at and think about for a sec, think before you speak, and then I'll ask. But I want you to think about what's being compared, because there's always two things being compared, right? On this one last time, it was the work days compared to the vacation day, or work months compared to vacation days, and it was now compared to later, okay? So what two things are being compared in this scenario? Don't say it out loud, just think it. Okay, somebody give me one thing that you believe is being compared. It's not a trick question, I promise. One thing. Park. The park to the map. And so I'm going to write just a little bit differently, but I'm going to write the real park, right, as opposed to the park that's listed on the map. So the real park compared to the map version. What else is being compared? That's the park compared to the map, so that's the same comparison, it's just the units for it. You're right, but something different. There's one more thing. Say it loud, Elizabeth. It's the length and the width. Okay, so these are being compared, and the length and width are being compared, or at least both talked about in the same fashion. Okay, so we're going to set up a proportion. We need to have one of these on one side and one on the other. One is a numerator and one is a denominator, and we get to make the decisions. So let's start with numerator versus denominator. What do you want to be in the numerator? There's 4 pieces. Just tell me one of them. The map version. Okay, so the map size of things. So do you want the map version in the numerator on the left to compare then on the denominator to the real version? Do you do it that way? Okay, so this is real life on bottom. So then from the left side to the right hand side of my proportion, what will I be comparing? Length and width. And it doesn't matter what order those are in either. I'll go with it alphabetical. Okay. There are 4 locations then that we are getting to put values. Each of the 4 locations will be each of the 4 values that we either know or want to find. So I'm just going to start on the top left. What is the map version of the length? 4 inches, yep. And for now, I'm going to make sure that I get all my units in there just to make sure everything lines up correctly and I don't inadvertently do something by mistake wrong, right? Okay, so let's just move down below it. Then what is the real length of the park? 500 feet. Okay, what is the map version of the width? We don't know it, right? That's what we're looking for. It's going to be in inches, though, so if you want to put inches next to it, you can. X inches. What is the real width of the park? 300 feet. Now, it's probably intuitive to most of you, but when you did decide that the length was 500 and the width was 300, why did you decide that? Yeah, just the way we constructed length and width, right? Like to talk about it, length is longer than width. So that's why that happened. Okay, and we're going to cross multiply, right? So if I start at the top left and I cross multiply down, I have 4 times 300. That's 1,200. I am ignoring the inches and feet because they will all cancel out, okay? Part of why I include them at the beginning is because I want you to see they're matching up. Here's inches and inches, here's feet and here's feet. So I don't really need to worry about them and multiply with them and so forth as I go. I'm just going to use the numbers. So I have 1,200. The other diagonal is 500x. What would I do last? Divide by 500, right? 500 and x are multiplied, so I'll divide to eliminate that. So what's 1,200 divided by 500? It is 2.4. So I'm going to write 2.4 inches, and then I'm going to sort of backtrack on something that I said in a different section and give context as to why. I don't remember which section it is, probably 6.2. I talked about the fact that however the numbers start, that's how the numbers should end. And by the way, we're working with fractions, so by golly, you better be giving me some fractional kind of answers, right? And those are all true statements, except that we're dealing with a real-life object. It's a map. And I don't know about you, but my rulers do not have fractions on them. They just don't. So it doesn't make sense to report this back in terms of fractions. Are you with me? Word problems are a little bit unique in that fact. We want to report them back in the way that makes sense for the context, and decimals make sense here. So 2.4 is what we're going to go with. Okay? We do want to make sure that we put the inches on there. We want the units to be present. So it is 2.4 inches. Any questions on that one?
How did the feet and inches cancel out?
Okay, so let me write them in so you can see them cancel out, but then please don't make me write them again. I mean, just because it's annoying to do so, but I'll show you how. Okay, so when we multiply, what actually happens is I ended up with a feet here and an inches here, right? Okay, so just pretend like this is multiplied feet times inches. I know it feels a little bit funny, but just pretend with me for a moment. The 500x was also feet and inches, right? But 500 was in feet, so when I divided by 500, the feet canceled, but they did so from both sides. Because I divided by 500 feet. And that always happens with the values as long as you've set them up in correspondence correctly. So I pay particular attention to the setup at the beginning so that I don't have to mess with the units through the problem. But then, of course, we want to make sure that at the end we put the units back on. Sound good? Okay. Next problem is a little bit trickier. It is very real world kind of thing, though. We have Kira and Dora. They worked 3.5 and 4.5 hours, respectively, on a programming project. They were paid $176 total for the project. Because Dora has fairness as one of her strengths, she wants to make sure that they're each paid according to the time they spent working. How much should each of them earn? So this is almost like real life of what would happen in my house, except that it would be like 3.5 hours for one of my children and the other one would be like, I'm done after 10 minutes. I mean, right? And so he should get something for doing something for the 10 minutes, but the 3.5 hours definitely deserves more, right? So how do you decide how much more? How do you make those calls? Proportions is a really good way to do this problem. And there's actually a couple of different ways to do the proportions for this problem that will work really nicely. So one way is to compare what Dora and Kira do individually, like make the comparison between the two people themselves. The other one is to make the comparison between what one of them does and what the both of them do combined and total. Does that make sense? The reason that I say that is because we don't actually know how much each one of them are paid. That's kind of the point. But we only know how much they were paid in total. Okay? So let me show you how it looks like if you set it up for the in total part, because I think the process makes a little bit more sense intuitively than the other one, and then I'll show you what the other one looks like, and you can see how it will work. So if we compare, it doesn't matter which one, Kiara's first on our list. So if we compare Kiara to what happened in total, okay, not comparing Kiara to Dora, but Kiara to what's happening in total, then what is the other comparison that we're going to make? The hours worked compared to what? What is it? What's the other comparison? The money made, exactly. Now, the problem is we don't know how much each girl made individually, but we do know the total amount of money that they had made, right? Okay, so how many hours did Kiara work? 3.5. The word respectively always means that it's in order. So Kiara is listed first, so her hours are listed first. Dora is listed second, so her hours are listed second. That's what that word means. How many hours in total were worked, though? 8. If you don't like the 3.5 as a mixed number, feel free to change it into a decimal. That's fine. Or an improper fraction. That's fine, too. We don't know how much Kiara made. We're going to figure that out. But we do know how much they made total. How much did they make total? 176. All right, so no matter which direction you're thinking of it, fractions, decimals, whatever, what is 3.5 times 176? Yes, 616. And then on the other diagonal, I have 8x. And if I divide by 8, what did she make? 77. Now, that doesn't answer the total question, right? It said how much should each one earn. So this is Kiara. How would we figure out how much Dora should make? Yeah, you guys are all saying it. Good. We're going to subtract 176 minus the 77. So how much will Dora make? 99. Okay, so this is one way to do this where we compare how much one of the people made to the total that's being done. Let me show you how it would look or how you'd have to think about it if you compare the two girls. Kiara compared to Dora. Now, the setup for the number of hours that they worked is very simple. I'll use decimals this time. 3.5 compared to 4.5. So that one's fairly friendly. But it's very awkward feeling to do the other side because I don't know how much either one made, right? I don't know how much, I do because we already did the problem a different way. But if we were starting with this problem in the beginning, I don't know how much either girl made. So what do I do about that? Well, what I don't want to do is create a variable x and a variable y because then I can't solve it. That's not useful. I need only one variable. So what I do instead is I create one variable x, and then the other one is 176 minus x. Because whatever Kiara made, Dora made 176 minus that. And I think that makes the arithmetic a little bit trickier here than the other problem because when I do my multiplication across this diagonal, I have to make sure that the 3.5 gets multiplied by the 176 and by the x, like distribution, right? So it makes it easier to make a mistake is what it really does. So when I have my 616, a very common mistake a student might do is just put minus x, but it's really minus 3.5x because the 3.5 has to be multiplied there as well. The other diagonal is the 4.5x. And when you add the 4.5x to the I'm sorry, I didn't want that. I wanted to add the 3.5x to the 4.5x. of course, you're going to end up back where we were in the other problem with 616 equals 8x. So they both work. I just think that this setup over on the right-hand side is just not quite as obvious as the setups in the other problem. And the arithmetic ends up being a little messier. All right, let's look at another one. At Rattlesnake School, the teacher-student ratio is 1 to 30. If the school has 1,200 students, how many additional teachers must be hired to reduce the ratio to 1 to 25? Okay, actually a very practical question when lawmakers decide to go changing like limits on teachers and things like that. How does it really affect, the number of teachers you have to hire? It matters, right? This is a big deal. So the things that are being compared here, what is being compared? How about teachers and students? Are you good with that? Teachers and students. I'm just going to do them as the fraction. What else is being compared? Now and later. And that's a little trickier in this problem because the ratio changes as well. So we'll get to the now versus later in a moment. But there's something else that's being compared too. Kinda. So in one sense, we're being told how many students we have, but in the other sense, we're being told the ratio. Do you see that? Do you know how many teachers there are? Did it say there are? Nope, didn't say how many teachers there are, right? So it's going to be tricky if I don't know how many teachers there are now to figure out how many teachers I have to hire later. So what I really need is I need to figure out how many students, so this is as a ratio. And then on the other side, so what is the, let me just pause right there. What is the ratio of students to teachers, or teachers to students, whatever? What did they give it to you? 1 to 30, right? That's the ratio. So this is my ratio. This is real people on the side. I don't know how many teachers I actually have in real people numbers, but I know how many students I have. What do I have? I have 1,200. So what this is going to allow me to do is it's going to allow me to figure out how many teachers I have. Okay? So that now later thing is going to come into play now, or come into play at this point. This is right now how many teachers I have. So let's figure that part out. Let's see, I have 1,200 on the top diagonal. And from the bottom diagonal, I have 30x. If I divide by 30, what is x? 40. So I have 40 what? Teachers. And this is what I have now. But I don't need to know just about now. I need to know about what I need to do for later, right? How does this scenario change if I change it to what I want it to be later? Sorry, a little louder. I'm having difficulty.
Wouldn't you just change the amount of students in the ratio?
Well, the students didn't change. Well, in the ratio, you mean. I'm sorry. Yes. Yeah. So it should say 1 to what, Elizabeth?
1 to 25.
Yep, 1 to 25. The actual student numbers don't change, but the teacher number is what's going to change. And just for the sake of making it not look like it was the same number, I'll call it Y. So this is what's going to happen later, what my goal is. So we'll cross multiply. So I still have that same 1,200, but now I have 25x. And dividing by 25. What is it? 48. So I have 40 teachers. I want to have 48 teachers. So the question actually asked how many additional teachers must be hired? 8. So we want to make sure we answer the question asked. The question asked is I need 8 additional teachers. All right, analyzing student work, it's a killer sometimes, I'll tell you what. So let's take a look at one where we're trying to figure out what's going on. Mary is working with measurements and writes up the following proportion. How would you help her? So her proportion says 12 inches over 1 feet equals 5 feet over 60 inches. Say it louder for me.
Just need to be together.
Need to be together, like, do you mean on the same side?
Yeah.
Okay, so what if then, if you're saying that, can I do this? Nope, so that's not gonna, I mean, you're right, that's one way to fix it, but it doesn't work the way I wrote it. So what else would I have to do? Cross multiplying won't help, because actually cross multiplying will show you that it doesn't really work, right? So the inches both need to be in the numerator. So if I did this, would it work? 12 inches, 60 inches, and 1 feet, 5 feet. Does that work? Yeah, that one works. And it's not the only way to fix it, but there is a problem with the way the problem's set up. Now, interestingly enough, each of the ratios themselves are fine, right? 12 inches and 1 foot, those are equal. 5 feet and 60 inches, those are equal. But the problem is that they're set up in reciprocal form from one another, correct? One of them is set up with the inches being compared to feet, and the other one is set up with the feet being compared to inches. So as we're taking a look at this, it's the setup compares inches to feet on the left, but feet to inches on the right. And it doesn't matter how we change it, but it needs to be the same. So if you were to fix it, we already did it, so down here, this would be one of several, but it would be one way you could fix it to make them be set up in the correct proportion. All right. Example 8. We have Amy. Amy's friend told her that the ratio of boys to girls in her classroom was 5 to 6. Amy was surprised that her class would have only 11 students. What would you tell her? Let's assume it's a traditional classroom. In some classes, 11 students might be completely reasonable, but the way the problem is questioning it makes it sound like that's not reasonable in her world. So what would you tell Amy? I feel like some of you are looking at me like, I know the answer, but I don't want to talk out loud. Be bold.
You can tell it just because the ratio is 5 to 6, just comparing adding 5 to 6.
Okay, so I like what you've said about the addition. That's very true. So let me start with how you've started. Just because the ratio is 5 to 6. I'm going to add one thing in the middle, though, Elizabeth. I'm going to say it doesn't mean there are actually 5 and 6 students. What else could there be? And still give you a ratio of 5 to 6. And so 5 to 6 as a ratio would look one way like this, right? So what else could you get to get you a 5 to 6 ratio and not end up with saying, yep, there's 11 students? 10 and 12 would work. because 10 and 12 is equal to 5 over 6, right, in a ratio form. If you did this, is that a more reasonable number of students? Probably. So if you really thought that there were 10 versus 12 students in this comparison, you could have a 22 student count if you did that. Anything else it could be? Starts to get big, but it could be. 15 over 18. So the thought here was that there were 11 students. How many would we get up to if it was a 15 over 18? 33 students. That'd be a very large class, but with student aides and so forth, it happens. Some of the kindergarten and pre-K classes will sometimes get that large. Yeah, something to look forward to for those of you in early childhood. 33 students. So the issue is simply that the 5 over 6s could be a reduced ratio, right? It could be taking the actual number of students and reducing the ratio down to 5 over 6. So let's tell Amy something like that. It could be, and you can take whichever example that you want. 10, what was it? Boys to girls. 10 boys and 12 girls, i.e. 22 students. Because 10 to 12 equals 5 to 6 as well. Or you could use your 15 and your 18 or whatever. Any of those would work and still give you that same 5 to 6 ratio. All right, so we know that there's a test coming up, right? When is it? It's Wednesday. So on Monday, we're going to be reviewing. So here's what I would like for you to do. I'd like for you to save the group work for this, but I'd like for you to do the homework. And the reason I would specifically like for you to do the homework is that way on Monday when we come to do the review, if you've had any questions from the homework, I can answer them, okay? And we can actually have a chance to go over them. But I'd like for you to have a chance to work in groups with the problems that are intended for group work as well. So I'm sorry that this is kind of flip-flopping the way that I normally would do it, but at least it's less to do over the weekend. I won't collect it on Monday, but if you choose not to do it by Monday, you've lost the opportunity to really ask me questions about it in class. So it's your call on that, okay?